Hello everyone, and welcome back to our series on sorting algorithms. Today we'll be covering a super interesting algorithm known as Bitonic sort. It's a little weird, quite funky, and of course very complicated. So let's just jump straight into it. Before we understand what Bitonic sort is though, we must first understand Bitonic sequences. More specifically, we need to know what a Bitonic sequence is and how we create a Bitonic sequence. These two pieces of information are crucial for understanding Bitonic sort, and so we'll be starting there. Beginning with the easier of the two. Put simply, a Bitonic sequence is a series of numbers that is first increasing and then decreasing. So 1, 2, 3, 3, 2, 1 is an example of a Bitonic sequence, since we start the list increasing and then switch to decreasing halfway through. This is just one example though, and you can see many more examples of Bitonic sequences on your screen now. If we wanted to get technical, we could say that formally, a dataset is considered Bitonic if there exists an index I for which all elements less than or equal to I are in increasing order, and all elements greater than or equal to I are in decreasing order. This formal definition also means that a list which is entirely increasing or entirely decreasing is also considered to be Bitonic. For the former, we simply consider the decreasing portion of the list as empty, and for the latter, we do the opposite. This comes into play a little bit later on, but for now, just know that we don't have to have both an increasing and decreasing portion of the list be full for it to be considered Bitonic. That's the gist of Bitonic sequences. They may seem useless now, but the entire idea of Bitonic sort is hinged on this idea of Bitonic sequences, and so they're essential. Bitonic sequences are, unfortunately, the easy part. The hard part is actually creating these Bitonic sequences, and that's how we'll actually end up using Bitonic sort. Before we get into any of the nitty-gritty details, I'm going to perform a magic trick. Stay with me here. Consider two integers. Any two integers. 5 and 10, 10 and 3, 800,000 and 9. Any two integers in the world that you can think of. Do you have them in your mind? Okay. Now with the snap of my fingers, I've converted those two integers into a Bitonic sequence. Don't believe me? Well, let's see. Say you chose 5 and 2. That's a Bitonic sequence, considering that 5 and 2 are in decreasing order, and we mentioned earlier that a list with only decreasing elements is still considered a Bitonic sequence. Okay, well, what about 3 and 10? Well, that's a Bitonic sequence too, considering that 3 and 10 are in increasing order, and we mentioned earlier that a list with only increasing elements is also a valid Bitonic sequence. Pretty cool magic trick, huh? In my opinion, it deserves a like on the video and a subscription, but hey, what do I know? Anyways, what was the point of this magic trick? Well, if any two elements are considered a Bitonic sequence, that means we can split any list into a series of valid Bitonic sequences. Then, if we had a method which could take two smaller Bitonic sequences and turn them into a larger one, then we'd have a way to convert any list into a Bitonic sequence, since we could continue to do this until the entire list is an increasing Bitonic sequence. That's essentially how we sort a list using Bitonic sort. Let me show you instead of just telling you. We start with the list and break it down into singular components. Then we group these components together into alternating increasing and decreasing pairs. We do this for every two-element pair in the list. Once we do that, we move on to combining each pair of Bitonic sequences into a new Bitonic sequence, this time containing 4 elements. So the first two Bitonic sequences would get combined into one larger Bitonic sequence, which is merely increasing, and the last two Bitonic sequences would get combined into a larger sequence, which is merely decreasing. Now, we have two Bitonic sequences containing 4 elements each. The next step is to combine these sequences into one final Bitonic sequence, which is only increasing. Once this is done, we have successfully sorted the list using a Bitonic sort. Another thing to note here while we have this pulled up is that you might be wondering what happens if we have a list in which we can't nicely break down the list into Bitonic sequences. For example, if we had a list of 7 elements, we'd only be able to make 3 Bitonic sequences, and then we'd be left with one integer left over. The same thing happens on, say, a list of size 10. We can make the first set of required Bitonic sequences, but then when we combine them together to create sets of 4, we're left with an extra Bitonic sequence that's left out. This problem actually brings up one of the biggest drawbacks to Bitonic sort, which is that it can only work on lists in which the size of the input is a power of 2. Datasets with sizes such as 2, 4, 16, 32, 64, etc. are the only sizes that work with Bitonic sort. This is most certainly not ideal, but we'll get into how it affects its implementations in computer science later on. For now, let's not get too bogged down in efficiency before we even know how the algorithm works. Tangent aside, hopefully now you can see the pattern which was developed. Break the list down into Bitonic sequences, and then slowly combine them into larger and larger ones until the entire list is an increasing Bitonic sequence. This process is split into 2 parts, what I'll call the Bitonic sort method, or the method which breaks the list down and sets up the framework, and what I'll call the Bitonic merge method, the method which builds the list back up. And so, after all that, we can finally formally define Bitonic sort as a comparison-based sorting algorithm which sorts a dataset by converting the list of numbers into a set of Bitonic sequences, and then combines those sequences to create a sorted list. Now, just a forewarning here, Bitonic sort includes a good amount of recursion, so if you're unfamiliar with the topic, check out our video linked in the top right, as well as in the description. Let's start with the pseudocode for the Bitonic sort method, or the one which breaks down our list of elements. The first thing to understand about Bitonic sort is that it takes in 4 variables, those being the array that we're sorting, which I'll call R, or short for array, a low index, a count integer, and a direction integer. Each of these has their own purpose, so let's break them down. Beginning with the array. This is just so that when we swap values, they will be swapped internally into the array that the user passed in. Later on in the example, you'll see that we visually create extraneous tables to show what's going on in the code. But the harsh reality is that everything is done internally and without extraneous arrays. Anything extra that's created outside of the original list is simply there to help with understanding. The low index is an integer which will represent the lowest index of the array or subarray that we're working with. The count integer is an integer representing the number of elements in the array or subarray that we're working with. And finally, the direction integer is something that will help us with determining whether or not we want to sort the list or sublist in ascending order or descending order. In this tutorial, a 1 being passed into the function will indicate that we want to put the list or sublist in ascending order and will be color-coded green. A 0 being passed into this function will indicate that we want to place the list or sublist in descending order and will be color-coded red. Those are our 4 variables. Now we're ready to get into the actual pseudocode. The Bitonic sort pseudocode begins with a base case. Again, recursion. Our base case for Bitonic sort will be if the count integer is greater than 1. Remember, the count integer represents the number of elements in the list or sublist that we're sorting, and so we'll break out of our recursive subcalls once this number is 1, since you can't really break down a list of 1 element into sublists. The first thing we do once entering this loop, after checking that our base case has not been hit, is set a new integer k equal to count divided by 2. Now your computer science anxiety might be acting up here, since you see an integer divided by 2. Well, what happens if we have 17 passed in as the count variable? Won't it mess up the calculations and throw off our entire code? Well, no. Remember, the size of the dataset has to be a power of 2. This means that every single time that this k variable is calculated, it will be an even number, down and down the subcalls until it's finally calculated as 1 and recursively passed into the function, thus hitting our base case. So while normally I'd advise against integer math like this, for today it's a-okay. So after we've calculated k, which, if you can't tell, is the median index of the dataset that we're currently sorting, it's time to recursively call Bitonic sort on the left and right halves of this list. So we call Bitonic sort twice, passing in r, low index, k, and 1 for the first call, and r, low index plus k, k, and 0 for the second call. This first call will set in motion a process to sort the left half of the list or sublist that was passed into this function in ascending order, and the second call will set in motion a process to sort the right half of the list or sublist that was passed into this function in descending order. This is all determined by the direction argument. Remember, 1 indicates an ascending sort, and 0 indicates a descending sort. The last and final step in our Bitonic sort pseudocode is to call Bitonic merge on the whole sequence of elements. Bitonic merge is the second of our methods, and the one that actually takes care of the sorting. We pass in r, low index, count, and the direction integer which was passed into this function. You'll notice that all of these variables are exactly the same as the ones that was passed into this Bitonic sort call. The purpose of this function will be to take the two Bitonic sequences which we've just created above and merge them into one larger Bitonic sequence. The direction of this Bitonic sequence, either increasing or decreasing, will depend on the direction variable that's passed into it. There is a lot going on here, and to be honest, it took me quite some time to figure everything out. So let's do something that helped me, and I think will help you guys a lot, and that's visualize these calls. So we begin by calling Bitonic sort on the entirety of the list, with 0 as the low index, the size of the list as count, and direction as 1, since we want to sort the list in ascending order. Once we do this, we have now set in motion a process to bitonically sort the entire list in increasing order, since the direction variable is 1. The Bitonic sort code will ask the computer to call Bitonic sort on the low half of the list, which will in turn call a Bitonic sort on the low half of that list, which will in turn call a Bitonic sort on the low half of that list, in which we eventually reach our base case. Remember, the goal of each of these calls is to sort the list in ascending order. This is because they're all a product of the first subcall in our Bitonic sort pseudocode. Once we hit our base case, we then go back up the list and slowly fill in the second recursive subcalls for each of these levels. So the far left Bitonic sort call has a recursive subcall, which wants to sort the right half of that list in descending order. Then, going back up one more level, this set of 4 subcalls has a right side call, which wants to sort the right side of the list of 2 elements in descending order. This recursive subcall then has 2 recursive subcalls of its own, which want to sort the left and right elements of this sublist in increasing and decreasing order respectively. Now we move back up the stack of subcalls and eventually reach our top level, which now calls upon a Bitonic sort to sort the right side of the initial list in decreasing order. Then this set of 4 elements will call 2 recursive subcalls on the left and right halves of this list, sorting them in increasing and decreasing order respectively. And finally, both of these 2 sublists will get broken down into 4 single element sublists, which we sort in increasing, decreasing, increasing, and decreasing order. This is the state that our list takes when it finally hits all of the base cases of our recursive subcalls. You can think of this as the product of the first half of the Bitonic sort pseudocode. The framework to sort the list is now put in place, and the next step is to go back up the list and sort it. This is where the Bitonic merge function comes into place. We take each set of 2 elements at the bottom of the stack of subcalls and merge them based on the preference of the call above it. For example, take these 2 elements on the far left here. If we look directly above them, we can see that when they were recursively called, the parent function wanted them to be sorted in ascending order. So we combine these 2 elements into a pair of elements which is in ascending order. Following that logic, the next 2 elements' parent function wanted them to be sorted in descending order. So we combine those 2 elements into a pair of elements which is in descending order. Doing this for the next 2 pair of elements on the right side gives us another set of elements in ascending order and 1 set of elements in descending order. Now we simply just move up the stack. The parent call of the 2 sets of elements on the left side wanted them to be sorted in increasing order. and so we merge them into a set of 4 elements in ascending order. In contrast to that, the parent call of the 2 sets of elements on the right side wanted them to be sorted in descending order, and so we merge those together into a set of 4 elements in descending order. Now the final step is to merge these 2 sublists into one main list, which is just sorted in ascending order, since that will be our complete sorted list. Hopefully this visualization helps you understand how the Bitonic sort function works. We break the list down into subparts using recursive calls of the Bitonic sort function, and then build them back together using the Bitonic merge function. Speaking of the Bitonic merge function, that's what we'll be covering next. The first thing to mention when talking about the Bitonic merge function is that it takes in 4 variables. These 4 variables are exactly the same as the 4 variables that were passed into the Bitonic sort function, those being an array to sort, an integer with the lowest index of the array or subarray to sort, an integer describing the number of elements to sort, and a direction to merge the list into. The first step in our Bitonic merge pseudocode is an if statement, checking if count is greater than 1. This is the base case for the Bitonic merge function. You might be wondering why we need recursion here, but that'll be explained later when we actually recursively call this function. So, if our base case is false, we create an integer k, which stores the count variable divided by 2. This will be the midpoint of the array that was passed in, and consequently the number which splits the first Bitonic sequence from the second. If we pull up an example list, you can sort of see what I mean. If the count variable, which we passed in, was 4, then k would be 2. K then defines how many elements are in both the ascending and descending Bitonic sequences that make up the list. Basically, k is a way for us to divide the list into its subsequent increasing and decreasing parts, which will become important very soon. The next statement is a for loop, which executes from the low index to the low index plus k using the index I. This will encompass the entire first Bitonic sequence, or half of the list. Now for each element in this loop, the element at index location I, we compare it to the element at index location I plus k. But the way we do this is really weird. Now the Boolean expression inside of this if statement will be if the direction element equals the Boolean result that comes from comparing if the element at index location I is greater than index location I plus k. If this expression evaluates to true, then we swap. If not, we do nothing. This is a whole bunch of complicated computer science jargon, so let me break it down for you in simple terms. Basically, we compare the element at index location I with the element at index location I plus k. This will systematically compare each element in the left side of the array with each element in the right side of the array. Pulling back up our example list, we can see what this means. In this case, when I is 0, we compare 1 with 7, and when I is 1, we compare 3 with 5. And then we stop, since we've reached 2. Nothing too complicated. Now if the direction variable is 1, and the element at the I index is greater than the one at the I plus k index, we swap. But if not, we don't swap. This is because if we are sorting the list in ascending order, we want larger elements on the right. And so, if the element on the left, the one at index location I, is greater than the element at index location I plus k, we need to swap it. If it's less than the element at I plus k though, then we can leave it alone, since it's already put in ascending order. However, now if we're placing the list in descending order, and the element at the I index is greater than the one at the I plus k index, then we don't swap. If we're placing the list in descending order, and the element at the I index is greater than the one at the I plus k index, we do swap. Basically, what this chart tells us right here is that if the result of comparing the elements agrees with the direction integer, then we keep them the same, and if they don't agree, we swap them. This allows us to maintain the Bitonic properties of the list. So let's add the swap statement to our pseudocode and move on. After this concludes, what we have is a single Bitonic sequence, created from the two that were passed in. The final step here is to call Bitonic merge on the left and right halves of this list. The first Bitonic merge call takes in R, the array, low index as the lowest index, K as the number of elements to Bitonically merge, and the direction as the direction. The second Bitonic merge call takes in R, the array, low index plus K as the lowest integer, K as the number of elements to Bitonically merge, and direction as the direction. The reason we do this is so that we can guarantee we have a sorted list. Bitonic merge takes in two Bitonic sequences and combines them together into one large sequence. But here's the thing. When this process concludes, we aren't always guaranteed a sequence which is correct. Take, for example, the two Bitonic sequences shown on your screen now. 1 and 3 are an increasing Bitonic sequence, and 8 and 4 are a decreasing Bitonic sequence. Let's say we wanted to Bitonically merge these two sequences into one increasing sequence. Well, if we follow the process for a Bitonic merge, we would end up comparing 1 with 8. And since 1 is less than 8, that agrees with the direction that we want, the lower number to the left. The same is the case for the next two elements we compare, 3 and 4. Since 3 is less than 4, that agrees with the direction that we want, and so afterwards we've ended the merging of our Bitonic sequence. But wait, 1, 3, 8, 4 is not an increasing Bitonic sequence, unless the rules of numbers have changed in the past few weeks. So what gives? Well, like I said, when this process concludes, the merging of the two sequences isn't always guaranteed to give us a correct Bitonic sequence. Now what it does do is get the list into a state in which we can recursively call Bitonic merge on both halves of the list, and eventually get into a correct Bitonic sequence. When we recursively call Bitonic merge on the 1 and 3 pair and the 8 and 4 pair, we pass in the direction that we want to sort them in this case increasing, and what this will do is shift the 8 and 4 pair to be increasing through the same process we described earlier. This will put the list of 4 elements into an increasing Bitonic sequence and complete the outer Bitonic merge. So that's why we recursively call Bitonic merge on the left and right halves of the list. This can get extremely confusing, trust me. In fact, on your screen now are both the examples I went through that helped me really figure it out. I actually had to do it twice since I misinterpreted the way the algorithm works and basically had to rewrite half of the script. Luckily for you guys, I'm going to now take this pseudocode and show you how Bitonic sort works in real time. And then after that, we'll enter a visualization of Bitonic sort to really show this algorithm at work on a large scale. So, pulling up a list of 8 elements, we can begin the Bitonic sort by Bitonically sorting the initial list in increasing order. Since the size of the list is still greater than 1, we haven't hit our base case, and so we Bitonically sort the left half of the list. We're still not at our base case, and so we Bitonically sort the left half of this list again, so that it's 2 elements. And finally, we Bitonically sort the list one more time to get it down into 1 element. Now we've hit our base case, and so we go back up the list to the list containing 2 elements and Bitonically sort the right side of the list. Now this sublist has also reached its base case, and so we now want to Bitonically merge these 2 sublists into a single Bitonic sequence which is in increasing order. So we run our comparison. 3 is less than 6, which agrees with the fact that we want the final list to be increasing, and so no swaps are necessary. Now that we've Bitonically merged these 2 elements, we move back up the subcalls and call Bitonic sort on the right side of the list with 4 elements. Then, since that list is still larger than 1 element, we call Bitonic sort on the left and right halves of this list. Both of those sublists are at their base case, and so we move to merge them back together. This time, comparing 5 and 7 actually disagrees with our parent call, since we want them to be in decreasing order, but they're currently in increasing order. So we swap the 2 elements, and that concludes our Bitonic merge. We can copy them up to the upper list and move on with our program. Now we must bitonically merge these two sublists of 2 elements into the main list of 4 elements, placing them in increasing order. So we start comparing. We compare the 0th element with the 2nd element. Since 3 is less than 7 and we're placing the list in increasing order, no swaps need to be made. Comparing the 1st element with the 3rd element though, 5 is less than 6, and that actually disagrees with the fact that we want the list to be in increasing order, and so we swap these 2 elements. Now we're not done just yet, since we need to recursively merge the left and right halves of this list. We start with the 3 and 5 list. Comparing the two leads to no problems, since they're already in increasing order. Now we focus on the 7 and 6 list. Comparing the 2 elements does lead to a problem, since we want the list to be in increasing order, and currently the elements are in decreasing order. So we swap those 2 values, which in turn completes this step of our bitonic merge. We can copy the values and move on. We've now successfully placed the left side of the list in increasing order. The next step is to go back up 1 level and call bitonic sort on the right half of the list. This time we want to sort the list in descending order. We recursively call bitonic sort on the left side of the list until we reach our base case, passing in 1 for each subcall until we reach it. Once we do so, we go back up a level and call bitonic sort on the right side of this list with 2 elements. Now that both of these sublists have hit their base case, we can call bitonic merge. Since we want to place the list in increasing order, the fact that 4 is greater than 1 disagrees with the parent call, and so we need to swap them to maintain the correct order. Let's now copy the elements up and move on. Next, we move back up the list 1 level and call bitonic sort on the right half of this list with 4 elements. This will create a decreasing sublist, and with it, 2 more recursive subcalls before we eventually reach our base cases. Merging these 2 cases together has us compare 8 and 2. Since 8 and 2 are in decreasing order, that agrees with our parent call, and so no swapping is necessary. Now that the left and right halves of this 4-element subarray are merged, it's time to merge the entire thing. Remember, we want this bitonic sequence to be in decreasing order. So to begin, we compare 1 and 8. This disagrees with our parent call, and so we swap the 2 values. Then we compare 4 and 2. This agrees with our parent call, and so we keep them the same. Remember, we're not done here though. We now need to recursively merge the left and right halves of this list. Starting with the left half, 8 and 4 agree with the parent call, and so no swapping needs to be done there. Moving over to the right half of the list, this time 1 and 2 do disagree with our parent call, and so we swap those 2 values to complete the bitonic merge. Let's copy the merged list of 4 elements up to the parent list and move on to our final step. So what we have now is an increasing bitonic sequence and a decreasing bitonic sequence. The last step is to convert these 2 sublists into one final main list, which will complete our sort. We want this sequence to be in increasing order all the way through. So we start by comparing 3 and 8. That checks out. Then we compare 5 and 4. This disagrees with our parent call, so we swap these 2 values. The next values we compare, 6 and 2, also disagree with the parent call, and so we swap those as well. That is also the case for our final comparison as well. 7 and 1 disagree with the parent call, and so we swap those. That completes the first level of our bitonic merge. Now, we move up to bitonically merging the left half of this list. Comparing 3 and 2 results in a swap, since they are in descending order, and 4 and 1 also results in a swap for the same exact reason. We then move on to the left half of this sublist. Comparing 2 and 1 results in a swap, since those elements are in decreasing order. Then we move on to the right half of that sublist. 3 and 4 do agree with the parent call, and so no swaps are necessary there. Then we go back up a level and bitonically merge the right side of the main list, the sublist containing 4 elements. Comparing 8 and 6 goes against the parent call, and so we swap there. 5 and 7 don't go against the parent call, and so we keep them the same. Finally, we move on to our final recursive subcalls. On the left side, we compare 6 and 5, which disagrees with the parent call, and so we swap those two values. Moving on to the right side, 8 and 7 also disagree with the parent call, and so we swap those as well. And with that, we have completed our Bitonic merge for the list of 8 elements. Copying our information up to the main array shows the complete sorted list. I understand that was a lot to take in. Having two functions which both use recursion really lengthens the process and definitely increases the complexity. But if you stuck through it, hopefully you now have a much better understanding of how Bitonic sort works. Now let's take things to the visualizer and look at this algorithm on a large scale. Running the algorithm on a dataset with 128 elements, you can see the process we just went through being absolutely eaten up by the computer. The formation of Bitonic sequences, and then the merging of those sequences can be seen pretty easily as the size of the lists that we're merging becomes larger and larger. And finally, on the last merge, you can see the two Bitonic sequences being combined into one large increasing sequence to finish it off. Neat. Okay, now that we have a pretty good indication of how Bitonic sort works, let's hop into the time complexity equations and analyze the algorithm in that sense. The time complexity equations for Bitonic sort are O log squared n across the board. Again, this is because no matter what state the list is in, we still perform a Bitonic sort and merge across the entire list. Unlike a selection sort or an insertion sort, we can't simply skip over elements just because they're already in the correct place. This makes it so that the entire process has a constant time complexity. For space complexity, Bitonic sort has an O n log n complexity, due to its use of recursion in multiple places. So now that you're seeing this, you might be wondering what makes Bitonic sort so special. If you remember back to the beginning of this episode, I mentioned that to use Bitonic sort, you needed to limit the size of your list to powers of 2. This, combined with its time complexity equations, which are nothing special, might have you thinking that this is just another algorithm. But I can assure you that that is not the case. While Bitonic sort does have a slower time complexity than some of the more popular algorithms out there, it's what's known as a parallel algorithm. Parallel algorithms are algorithms which can do multiple operations in a given time. For Bitonic sort, it works a little something like this. When we run the Bitonic merge function, we compare the first element of the first Bitonic sequence with the first element of the second Bitonic sequence. Since this is a predefined comparison sequence, we are not reliant on the data that needs to be sorted. In a list of 8 elements, the 0th one will always be compared to the 5th one, the 1st to the 6th, the 2nd to the 7th, and so on and so on. What this means for us is that we can actually run the algorithm on multiple processors to make things go exponentially faster. This is really good for us, since it helps us sort the data faster. So while the equations might not make it out to be a hyper-efficient algorithm, it has the potential to be one, due to the fact that we can do the work on multiple processors. It's like having a group of 5 okay-ish workers doing an assignment, rather than one really good worker. The one really good worker is better, but the 5 okay-ish workers will get the job done faster. It's just a matter of whether you're willing to pay for the 5 okay-ish workers. And that takes care of the common implementations of Bitonic sort as well. It is a general-purpose sorting algorithm which really shines when it can be run on multiple processors. And with that, we are finished today's discussion. To review, Bitonic sort is a comparison-based sorting algorithm which sorts a dataset by converting the list of numbers into a set of Bitonic sequences and then combines them to create a sorted list. Sorry for the delay in this video, by the way. Midterms and schoolwork have finally caught up to me, and this one took a lot longer than expected. But be sure to tune in next time when we talk about another sorting algorithm. Thanks for watching.